Hello everyone, and my name is Matt Farrell, and today I'll be discussing a paper titled Reusing Debugging Knowledge via Trace-Based Bug Search, written by the authors seen here, all from the Department of Computer Science at UC Davis. Note down any questions or thoughts you might have during the presentation. I'm happy to answer them via email or via the mailing list for the class. So with that, let's get started. In your experience as developers, I'm sure you've come across a number of bugs. Trivial or not, your first thought, if the answer was not immediately obvious, to quickly grab critical line of a crash stack trace and Google it. I know I've done it thousands of times, and the researchers, as well as I, have found that this provides surprisingly good results a large amount of the time. The research in this paper attempts to address the issue of these millions of similar bugs that exist in millions of projects and provide an easy-to-search repository to find the answers as quickly as possible. Instead of you having to do the analysis on a trace, on a bug, the procedure and the tool in this paper provide the automation of such a search using a custom collection engine to get the relevant bug data, a query language for finding similar bugs in the database, and an interface to make it as simple as possible to get fast results. This takes the guesswork out of your analysis for the trace and allows an objective comparison by the system only on the relevant data instead of the entirety of Google. Well, how does the tool do it? Well, Oscilloscope is the tool introduced in this paper and provides the previously described bug searching automation with four important parts. The trace collector will gather both stack and execution traces from your application and store them for analysis later. The bug database is the core of the system, holding all the previous resolved and unresolved bugs that have associated traces that we can match a new problem with. BQL is short for Bug Query Language and offers a language for querying the bug database that's based off of SQL and allows us to refine those searches as much as we want to better fit our specific bug. Lastly, we have the UI itself, which tries to make itself as accessible as possible with an Eclipse plugin, offering instant searches on the bug database. And you can also integrate that directly into your JUnit test cases to make them more powerful. To get a better idea of how this will work, let's take a look at a simple example. Here you can see a trivial sample of the usage of the lazy dynabean class, where we set a property of the instantiated object to null. Without knowledge of the API, you might expect running that and running a get on that same property would return null since that's how we originally set it, but in fact the class will initialize missing keys for you to a non-null value. The scenario has occurred many times for the dynabean class, and the bug repository contains a few instances of this non-issue. Instead of a developer having to take the time to explain yet again why this functionality is intended and the resolution of simply extending the class, it could have been found in seconds by a developer using Oscilloscope to search the repository for similar bugs to what they were encountering. This provides a quick sample of how the turnaround of a solution could be drastically reduced. In this particular case, an answer is given in seconds instead of the developer taking a few months to get back to another duplicate of this. Now, to get to these results, we need to take a little deeper look into the setup of the Oscilloscope system. Here you can see a diagram with the overview of the system in some basic terms. The bug traces are sent off to the Oscilloscope plugin, which then uses either default or manually added BQL queries to search on particular parts of that trace, and that's usually the suffix but not always. The Eclipse plugin provides quick access to the data by allowing user to begin a record of their application, trigger the bug in the system actually happening, and then search on that trace instantly. The database will be more powerful as it gains more and more knowledge about different bugs that might exist. And if these results aren't granular enough, you can actually drill down into the tracing code and specify on a statement method level if you have that availability in the code. Even options exist for setting chop points where the execution would begin and end for trace collection and would allow you to improve results even further so you can get some better insights from the database. Quickly, I just want to mention that the usage of the term bug here could be in question. So, as defined by the authors in the paper, it is a behavior that violates a user's requirements. This definition uses some keywords which would probably better map to a failure for the nomenclature we've utilized in class, but I utilize the term bug in this fashion for the remainder of the presentation just to remain consistent. Oscilloscope provides some predefined BQL queries to help with basic searches as well, mostly suffix-based. Another key point on this slide is to better understand some of the evaluation later, there's the Levenstein distance. This distance is user specified and is the minimum number of substitutions, deletions, and insertions to rewrite one string into another. So with this, you can see by how many steps one trace will vary from another and provide results only within that range. Increasing the number will allow more results and potentially more false positives. Also, since bugs are compared in pairs by the tool, it introduces a great opportunity for strategies such as MapReduce and other advantages of highly distributed systems. With the important notes of the underlying query engine out of the way, we can take a look at some of the challenges the authors faced. When looking at the data the writers collected, they noticed, based on the stats they ran on the bug traces entered, they would have some issues with running comparisons on extremely large traces. It would be partly performance and partly because the Levenshtein distance between these two traces could be misleading if too much data is given to compare. To produce better traces for storage, post-process method traces were analyzed, and sometimes contiguous blocks of method-level traces were replaced with just the name of the class or the package to make it give some more accurate comparisons. As mentioned earlier, adoption levels are key. The more bugs, the better. So making BQL SQL-based made it a little easier to adopt. And lastly, instrumentation overhead adds some complexity to this process. So the chopping ability, where you can set where those traces begin and end, allows you to limit some scope and help mitigate this issue. Expansion into concurrent applications may be difficult too, requiring some refactoring to account for the multiple thread tracking. With those in mind, let's take a look at how they evaluated the tool. Looking briefly at their test setup, we can see that they collected a number of method-level traces and went over the majority of them manually. These traces were taken from reports on bugs from the Apache Commons library and Rhino, which were only decided upon based on popularity. While not all bugs were taken, since some limitations existed on the availability of tests to generate the stack traces, you can see the numbers that were taken from each one as a test sample. Also in the chart provided some basic statistics on those reports and how the trace lengths broke down. First, we know that to test the system, we need to know if it's accurately finding similar bugs to those under test. So by running the tool and finding sets of all similar items, we can first comb over the output of the tool to discover potential false positives, putting aside false negatives for the moment. Some numbers for the initial run showed that 273 of the total bugs were similar, and 74 of those were actually identical. Presents a question of what we could consider similar and how we're actually judging that. So, along with measuring what when we find resolved bugs matching unresolved ones, that would be the ideal situation for an end user. To test the configurations on these types of metrics, the writers would vary the suffix comparison length, which lets you compare more or less of the actual end of the trace, and the Levenshtein distance, as mentioned before, to help find the ideal matches and the number of changes we need to get from one to the other to find the best results from the data set. Precision and recall were the important metrics for this evaluation. Precision being the ability to accurately identify bugs that are actually related with as few false positives as possible, and recall being the ability to find all those who should be found out and leaving out as few relevant results as possible, which will handle the false negative side of things. The evaluation here used slightly modified versions of these pure terms, as it was somewhat unfeasible for them to run them against the entire set of bug traces, so a resolved precision and a relative recall were used. It only resulted in a possible slight over-approximation of the recallability of the tool, but still represented solid results. Now for the results of the evaluation. First, a note on one important stat on this chart that's new is the rightmost column, called the F-score, which the researchers created as, in their own words, a harmonic mean of the precision and recall. The idea was to provide a combined metric for a simple view of weighing the two metrics evenly, making an easy reference for which configurations were superior. As you can see, the important result from this analysis was that the oscilloscope tool had a high recall and precision score under a number of configurations, but a clearly superior when run with the 10 Levenshtein distance and the 50 suffix length. To further support oscilloscope, a couple extra tests were run. The first checking for duplicate bug traces in the set of analyzed items from Apache and Rhino. In there, they were able to find about 33 duplicate bugs, with 28 already marked as such in the tracking systems. The other 5 were manually examined and found to indeed be duplicates, one of which was actually verified by one of the developers of the system. The second test here gave a quick F-score comparison just to show that execution traces run superior to stack traces when doing comparisons, even though they take a little more time to run. The remaining question on the tool is how much it'll run under large numbers of bug reports, and the scalability results here show us that if we took all of the bug traces in the database and just kept replicating them until we reached the desired database size, the search methods being based on Hadoop paid off greatly and allowed the distributed systems to really give us good times on getting back results, even when the data was growing exponentially. To wrap things up, the oscilloscope tool showed us strong results under both conditions presented by the researchers for precision and recall. The analysis of the top configuration of the tool was utilized on some mature projects which revealed duplicate bugs, and in turn showed the ability to help identify solutions for users who may have similar issues. The small size of the database could actually be a testament to the software's ability, since under larger sizes the database and the tool are actually going to be much more useful, so the small set still provides quality results is somewhat telling. Some shortcomings for the tool: basically, bugs that don't cause termination can be much more difficult to find solutions for. This is because of the suffix-based approach of the tool, especially in the default setup. The more knowledge you have about BQL and domain knowledge, the more you're going to be able to mitigate this issue with some custom queries to suit your needs and be able to find those actual problems in the middle of the trace. Next, sharing of prefixes on a trace can generate high numbers of false positives simply because it can lower the Levenshtein distance between your trace and another trace, even though they both may be unique, and the actual error is lower down in the trace. Limiting scope can mitigate that as well. Lastly, the subjects studied are admittedly limited, and the two under study here may not be representative of all software out in existence, so the quality may not hold up if tested on a wide variety of software. Thank you all for listening. As mentioned earlier, I'm happy to take any questions via email or the mailing list. The following slides after this one, I have a couple discussion questions I came up with. Each slide has a question, then I'll advance the slide to show my thoughts. So whoever's controlling the audio is welcome to pause after I flip to the question, and then resume after you guys have had whatever discussion to reveal my thoughts. For this question, expanding oscilloscope to other areas of interest could run into some difficulty when utilizing languages or environments that don't lend themselves to high traceability. Lower level languages could be especially tricky and require large amounts of refactoring in the tool to make it work effectively. The authors also mentioned the tool was not particularly suited unless it was highly customized for traces and errors that didn't terminate execution. With that in mind, any highly robust executions could present traces that may not end up matching well with those in the database, since the suffix could be quite different and not represent the actual error. For this question, some of the updates to projects which we'd be searching on would immediately show some issues with any new package names or class names that were introduced with the updates. Since the system relies upon the Levenshtein distance, it could create an inflated distance number and create higher numbers of false negatives. The conversion of taking existing data sets of bug traces would likely not be easily converted, and perhaps not worth investing the required amount of effort to retrofit the database contents for searching.